So the limit comparison test worked well, and we didn't have to mess around with the direct comparison. So let's keep practicing it for other problems. All right, so I have 1 over 3 to the n minus n. Now, before I go off and start dividing and all of that, I want to think about what I'm looking at. So if I look at that a sub n, I want to find a comparable series. So find a comparable series, comparable, either way you want to pronounce it. Okay, so our a sub n is 1 over 3 to the n minus n. Now, if you think about where you're heading as you head to infinity, the 3 to the n is the important part. The minus n isn't going to do anything, right? The exponential is way bigger than that power. So that's similar to 1 over 3 to the n as n goes to infinity. That's an infinity. There you go. Okay, so then, well, 1 over 3 to the n, that is the same thing as 1/3 to the n power. Okay, so maybe that's my comparable series right there. 1/3 to the n. Let's let that be b sub n. Okay, so b sub n would be 1/3 to the n. And why am I excited? Well, because that is a geometric series, a convergent geometric series at that. Right? So, and the reason it's geometric, well, it's geometric because it fits in the style a times r to the n, but it's convergent because r is 1/3, which is less than 1. Okay, so now I can use all of this to do my comparison. So I want to take the limit, sorry, I've lost all my pens here. The limit as, well, I'll just do it in blue. Oh, here it is. The limit as n goes to infinity of a sub n divided by b sub n. So I guess I'll just call this a sub n, and I'll call this b sub n. Which one is actually a sub n, which one's b sub n is not dictated to us by the theorem, so you actually can reverse them if you so desire. All right, so I'm going to take 1 over 3 to the n minus n, and I'm going to divide it by 1 over 3 to the n. I'm going to use this form just because it's similar to the form that I've got. No good reason other than that. Okay, so this is the limit as n goes to infinity of 1 over 3 to the n minus n times 3 to the n over 1, which is the same thing as the limit as n goes to infinity of 3 to the n over 3 to the n minus n. And that's setting off little alarms in my head because that's infinity over infinity. And this is not going to work out with that table that we used on the previous page. The table one is for when it's a rational function. So if it's a polynomial divided by a polynomial, x to some power over x to some power. That is not what we have in this problem, or in this case would be n to a power. So we are not able to use that table. We're actually going to have to use L'Hopital's rule. So I'm going to apply a L'Hopital's rule and take the derivative of both of these. Well, the derivative of 3 to the n, can't forget my limit as n goes to infinity, is the natural log of 3 times 3 to the n over the natural log of 3 times 3 to the n minus 1. Okay, well, that's still infinity over infinity. I'm going to have to do L'Hopital's rule again. So I guess I'll just do it right here. L'Hopital's rule, make sure you put L'Hopital, or L apostrophe H works as well. And we'll say limit as n goes to infinity. All right, well, the derivative of 3 to the n is still 3 to the n times the natural log of 3. And I have another natural log of 3 sitting there. So it's going to be natural log of 3 squared times another 3 to the n, right? So it's 3 to the n, natural log of 3, and another natural log of 3, because there's this natural log of 3 sitting there, and then there's another one when you take the derivative. Same thing down here. It's going to be natural log of 3 squared times 3 to the n minus 0, so that's all gone. Hey, you know what happens? Natural log of 3 over natural log of 3 squared over squared. It's gone. Makes 1. 3 to the n over 3 to the n makes 1. So this limit is 1. And 1 is a finite number that's not equal to 0. I should have written that on the previous one. Technically, 0 is a finite number. However, it's a finite number that's not equal to 0. Right? Because 0 is finite, but it's not one that we want. All right, so finite number not equal to 0. Yay. And that means that both of these will converge. And so therefore, now keep in mind, I have to not only find b sub n, I have to argue that it's convergent and prove it. So I have to do this bit up here, find my b sub n, prove that it converges, then go find my ratio, the limit of my ratio, which means multiple applications of the L'Hopital rule in this case, L'Hopital's rule I should say, and then that means they would both converge. This one's converging because that one's converging and we have a finite number here. And you have to have all of that there. Okay, now what about the next one? Well, it's a little tricky. So we kind of want to remind ourselves of some things here. So if I look at a sub n, which is 4 to the n, 4n squared, I'm sorry, 4n squared plus n divided by the third root of n to the 7th plus n cubed. Well, at its heart, as n goes to infinity, the ones that are going to win are the 4n squared and the third root of n to the 7th, right? This part's not going to matter as we go to infinity because that n to the 7th is going to be infinitely bigger than that one. So it's, again, that comparison of rates of growth, that thing that we talked about in 10.2. So this is similar to this. But a root is a power written a different way. So that would be equal to 4n squared over n to the 7 thirds, which would be 4 times n. 2 take away 7 thirds is negative 1/3. So it's 4n to the negative 1/3, which would be 4 times 1 over n to the 1/3. All right. A couple things to remind ourselves really quickly of. Let me just kind of throw this in over here. A couple things. I did the n. If I have n to the p over n to the q, that's n to the p minus q. So that's where I'm getting the negative 1/3 from, because I'm taking 2 take away 7 thirds, which makes negative 1/3. And negative 1/3 means it's 1/3 in the denominator. Similarly, n to the negative a is 1 over n to the a. And then also, if I have the qth root of n to the p, that's the same thing as n to the p divided by q. Just a little pre-algebra reminders of some things for us. All right, well then this is my b sub n right here. I've got b sub n right there. The 4 is kind of irrelevant. What matters to us is that n to 1 over n to the 1/3. Now notice that is a divergent series. So b sub n, which is 1 over n to the 1/3, is a divergent p series. It's divergent, and of course I would have to explain this, because p is 1/3, which is less than 1, right? In a p series, when your power is less than or equal to 1 is the harmonic series. So less than or equal to 1 it diverges, greater than 1 it converges. All right, so then I can use all of that to inform my selection. So I'm going to take the limit as n goes to infinity of, this is going to get interesting, 4n squared plus n over the third root of n to the 7th plus n to the 3rd divided by this lovely series over here, which is 1 over n to the 1/3. Okay, so that's the limit as n goes to infinity. 4n squared plus n over third root of n to the 7th plus n cubed times n to the 1/3 over 1. Distributing that in, that is equal to the limit as n goes to infinity. I'm just going to start rewriting this denominator 1 as a 1/3 power because I know I'm going to need to in a while anyway. So it's n to the 7th plus n to the 3rd all to the 1/3 power. And then over here, remember what happens when you multiply powers. In fact, I'll just add that into our list. N to the p times n to the q is n to the p plus q. So I'm going to add those powers. So it's going to be 2 plus 1/3, which is 7/3. So that's 4n to the 7/3 plus n to the 1 times n to the 1/3 would be n to the 4/3, right? 1 plus 1/3 makes 4/3. Okay, well, this is all well and good, but we're going to do a little bit of, algebra. We're going to factor. I'm going to factor out an n to the 7/3 because I can see I have a 7/3 here, and in the end, I'm going to have a 7/3 here. So I'm going to kind of do some math work here to kind of, factor it out. Okay, so let's see here. I'm just going to do this. All right, so this is the limit as n goes to infinity. I mean, technically, we could use L'Hopital's rule. It's infinity over infinity, so we could do that instead. But I don't want to bother because it's not gonna go nicely because I've got a lot of powers in here and I'd have to use chain rule down here and it'd just be a thing. So I'm instead going to use a little bit of fancy math. So I'm going to start with the numerator. I'm going to factor an n to the 7/3 out of that numerator. Sure, why not? So in that first term, what would be left? 4, right? So you took the n to the 7/3 out. You're dividing it out. All right, and then what's left here? Okay, so that would be n to the, I want to take 4/3 and take away 7/3. 4 take away 7 is -3/3, or -1. Now remember, you should be able to multiply and get back what you had. 7/3 plus a -3/3 makes 4/3, right? It works. Over, all right, now if I take, let me just take the n to the 7th out. So if I take an n to the 7th out, that leaves me 1 in that first term, plus an n to the -4. Same principle as up above, right? 7 plus -4 would make 3, right there. So 7 and -4 makes 3. I'm factoring the n to the 7th out. So I'm taking 7 away. This one only had 3 to give. So I'm at -4 in the whole, right? It's a little easier to see, I think, in the denominator. All right, so that's to the 1/3. So let me distribute that 1/3 real quickly. So that's the limit as n goes to infinity of n to the 7/3 times 4 plus n to the -1 over n to the 7/3, right? 7 times 1/3 makes 7/3. Again, real quickly, n to the p to the q is n to the p times q. So I'm using that property right there. Sorry for that one. Just a little pre-algebra reminder of your power rules. All right, so then that would be 1 plus, right, because 1 to the 1/3, right, you're factoring that out, right? So n to the 7/3, so I distributed that there, and it'd be 1 plus 1 over n to the 4th. Actually, I'm just going to leave it as a negative power. I won't even bother rewriting it that. Since I wrote it as a -1 right there, I'm going to write it as -4 right here to the 1/3. All right, well, the reason I did that was because these are going to go away. And that's going to leave me with 4 plus, this is the limit as n goes to infinity. Sorry, I'm having problems there. Limit as n goes to infinity of 4 plus 1 over n over 1 plus 1 over n to the 4th all to the 1/3. All right, this is not indeterminate. It was until this point. So if you look here, that's infinity over infinity, every which way. This is infinity over infinity. This is infinity over infinity. But I'm not using L'Hopital's rule because L'Hopital's rule would be a mess, right? Chain rules and all that. So I'm instead using algebra. I factored, I canceled because they both had a 7/3 in there. So I canceled out the 7/3 and it left me with this bit left over, and then I just rewrote that bit. But if I put infinity in here, think about what that means. 1 over infinity, we learned a long time ago, that's 0, right? So this would be 4 plus 1 over infinity over 1 plus 1 over infinity to the 4th power, which is infinity, to the 1/3. That's 0, that's 0. So you're left with 4 over 1 to the 3rd, which is 4 over 1, which is 4. That's your L. Notice it's a finite number that's not equal to 0. Yes, you have to say that. And therefore, A sub n converges also. Because B sub n, diverges, my goodness, diverges. B sub n, I'm glad I looked up. This one was divergent, so therefore this one diverges. They go together. It doesn't matter if it's, it doesn't matter that it's a finite number here. What matters is, since this one's divergent and it's a finite number, then this one diverges also. So the ugly one diverges because the simple one does, and the limit of this is a finite number.